All right. Oh, I'm a little taller than Rachel. Who knew? I think I'm going to take this down. If it all goes terribly wrong, I promise to return it to its rightful place, okay? That's more like it. All right. My name is Sarah Tuttle. I'm here to talk to you about dark energy. Now, when I saw the other people talking tonight, I died just a little bit because I have nothing to explode. There are no feathers. You guys, dark energy is made up. Okay, so that's cool. Instead, we're going to learn how to be astrophysicists. So how many people here would love to leave today knowing how to be an astrophysicist? Ah, sweet. Good. I can retire. Problem solved. So we're going to have this little talk. There will be some yelling. You seem good at that part. That's the best part of the third talk at a bar. So, because there are no good pictures of dark energy, it's very elusive, and the paparazzi are not as talented as we had hoped, instead, we're going to talk about the entire universe. We'll get around to some dark energy. Again, there'll be some yelling and some prizes. So let's see what we can do. Right, yeah, I know. Have more alcohol, it's a great life plan. So, let's start out with a question. What is the universe made of? Oh, you're so good at this yelling. I know. Yeah, I gave you some prompts. All of those things. Stardust, I like it. Otters, true fact. Atoms and molecules. We have swans. My son's going through a swan phase. Booze. Yeah, that's the truth. Certainly in here. It blows up. It makes stars. It's perfect. We have the Helix Nebula. That's a planetary nebula. All those things, right? So we think we've got a pretty good gauge on it. We have scientists who study a bunch of those things, even things like dinosaurs. Otters. Good. Let's see what we can do. One of these buttons is the right button. Let's find out. Not that one. Oh, yes. Good. All right. So then, it turns out astrophysicists are really just accountants with chalk. So here you can see the universal energy budget. We went and did a little accounting. We looked for all those things you talked about. We looked for atoms and molecules and gas. We looked for swans, and we found there are almost none of any of those things. Or we're very bad at counting. We found that, in fact, most of the universe, almost 70%, depending on which theorist you happen to enjoy at that moment, is dark energy. Dark energy is what we like to call a placeholder. That means we don't know what it is. We're really sorry. We hope you don't notice this vast chunk of the pie chart that we cannot explain. We're going to go back here and fix it. 27% is dark matter. We're going to talk a little bit about dark matter and dark energy because astronomers, besides being accountants, are also really bad at naming things. You can tell because we've named these two things that aren't really related except for the fact that they're in the universe, basically the same thing. So that happened. Dark matter we can measure. We know dark matter exists. We don't know what it is. We have detection experiments that are trying to understand what particles make up dark matter. But that's a thing, so that's encouraging. It can look like chocolate cake. That leaves only 5% of the entire universal energy budget for otters. I'm a little disappointed, but I've already got a PhD, so I guess we'll soldier through. Now we're going to play a game. We're going to say 3 volunteers who are feeling sprightly and like running and making executive decisions. Yes, sir, come on up. I'm going to need 2 more. Yes, young man, come to the stage. All right, run on up here. What's your name, sir?
Fatty.
Fatty, thank you for joining me. And you, sir?
Rin.
Rin, okay, are you guys ready? Maybe we need 1 more. This is a bigger group. Big group? Ma'am, yes, come on. Oh, they're fine. Anybody. You love running. Okay. You're going to grab this pile, sir. Okay. You take this pile. Now I'm going to trust you guys. This is Austin, so you're going to have to do some sort of, like, consensus bullshit. I don't know. Figure it out. There's a lot of people out there. I'm going to ask them if something is dark matter or dark energy. Now, before I start, you guys should kind of move into the crowd. When you hear someone give the right answer, you can give them a prize. Okay? There are 4 things, so don't run out too fast. Yeah, be cautious. So run on out there. Go on. Spread yourselves out. Chip chop. Fantastic. Great. Give them a round of applause for tolerating that. Now, I've given you some time so you can, get ready for quiz time. I hope you feel armed and ready. All right, wait. Now just wait on it. You don't want to get ahead of yourselves. Dark matter or dark energy? Ooh, you're so good at this. I think you guys have been on the interwebs. This is dark matter. This is a galaxy cluster. The blue gas in the middle, well, it's not really gas, it's dark matter, but it's been made that way by computers, or as Fox News would call it, false colors. Dun, dun, dun. You guys, it's all false. No one can see in X-rays or gamma rays. We just use computers like smart people. Okay. Here's another one, dark matter or dark energy. Oh, I'm so mean. Not otters either, I know. This is dark matter. This is an experiment called LUX. It is a direct dark matter detection experiment. Spoiler alert, it has not figured it out yet. And you can actually see here, we have these experiments that use liquid xenon. You cannot get that at Costco. To try to wait for dark matter particles to encounter the xenon and decay, and you can see then it would hit detectors, and then we'd be able to find out what the particle was. Wouldn't that be cool? Totally cool. We haven't done it yet. All right. How about that one? Oh, you guys are so optimistic. I love you right now. No, this is dark matter, but good try. Yeah, so this is a gravitational lens system. Is there a magical lady thing? Nope. Okay. Oh, does this do that? Let's find out. Oh, I bet it. Wait. Oh, yes. So can you guys see these kind of weird schmeary-looking galaxies? Right? They're like arcs. Cool. So that is a big galaxy cluster. What you cannot see is the giant lumps of dark matter that are there with it. And what's happening in this cluster is that light from galaxies way behind it, that are in these lovely little galaxies here, are coming and being bent around the giant lump of dark matter and also light matter. And look, you can see it. So again, false color, yada, yada, we can't see dark matter, but we can make models of where the dark matter is distributed in the cluster. Okay, so that's pretty exciting. We have one more, people in the audience distributing prizes. How are you holding up? Yeah? Yeah? Okay, now's the time. You ready? This is the last one. You're doing great. Do some people have prizes? Nice job, team. Okay. I love it when people participate. Great. Okay, last one, go. Oh, you're so good at this. I am proud of you all. I am proud. Give yourselves a round of applause. All right. I brought some plots. I'm a physicist. We make plots. My mom used to put my plots on our refrigerator. It was the cutest. She's like, I don't know what it is, but it's all you did today, so. So it turns out, although I'm making fun, dark energy is not just theorists with pencils who are trying to keep the rest of us busy, although that would frankly be a really good idea. Instead, we have observations that tell us about the history of the universe, that tell us about cosmology, because we want to know what's happening. Is the universe running out of energy? Should we all go buy a lot of water from H-E-B tomorrow? Is the end coming? The dinosaurs, there's just a lot to worry about. So we study cosmology. Humans have done this forever. Again, I think it mostly is to keep many of us out of prison. I feel good about it. Here you can see why cosmology is complicated. So on this plot, which is looking at two different cosmological variables, you can see there are 3 different colors and 3 different shapes. Each color and shape is a different kind of experiment. So the orange down here is the cosmic microwave background. The blue are supernovae, in particular type 1a, or as we call them, Jeff supernovae. And BAO, the baryon acoustic oscillation. And what you'll see on this plot is that those areas overlap in a pretty small region. So this means to make these measurements of cosmology, or the history of the universe, we use vastly different kinds of experiments to try to pin down the values. And the reason that we do that is because the universe is not tiny and is not happening in a single moment. So we need to probe over the volume of time and space to understand what's happening for the history of the universe. All right, now come the Nobel Prizes. That's like the best part, right? No, although they do give you some money and a shiny gold coin, so, This is the cosmic microwave background. This is really cool, and for this next chunk of the talk, I want you to think about theory and observation. because that's really the tools we have. Astrophysicists are really weird physicists because we rarely get to set up experiments in our lab. Instead, we have to go and poach experiments from the universe. So sometimes they get a little sloppy. So here we have a plot, one of my favorite plots, from XKCD, which is a comic. And you know, it's a classic, what can I say? But here's why it's exciting. Because the theory from this plot, which is the equation at the top, matches the experiment almost exactly. And in fact, that plot, although hand-drawn, has error bars on the points, but those error bars are so small that you're not able to see them. So what's it a plot of? It's a plot of the cosmic microwave background. Who here has heard of or knows what the cosmic microwave background is? Oh, you're all hipsters that own tube TVs, aren't you? That's what I thought. So the cosmic microwave background, people sometimes refer to as a baby picture of the universe. This is radiation from the very beginning of time. And it turns out that we're actually able to observe it as it has cooled through time. Now, let's be a little bit honest. That's pretty weird. And it was only thought of in like the 1960s. So by then, we already knew that the universe was expanding. I don't know if you knew that. If you did, awesome. If not, sorry. So the universe is expanding. Everything's moving away from everything else. We're sort of moving along. But there were some debates about how that was happening, how the universe started. And there were two big theories that were happening. There was the Big Bang theory, and there was the steady state theory. So people were trying to figure out, how can we prove it? And some theorists were like, you know, I think if there was a Big Bang, we should have some residual radiation that we should be able to observe, right? So there's like 4 guys in Princeton. They're really busy. They're using a lot of number 2 pencils. Meanwhile, there are 2 guys at Bell Labs, and they're trying to make this complicated experiment using an old radio telescope out in the yard. They have been very careful. They're trying to reduce this data. The data will not comply. This is like everyone's nightmare. You're like, we did this really carefully designed experiment, and nothing's working. So they had this signal, and they couldn't get rid of it. They turned it off and on. They kicked it. They wiggled the wires. They had no luck. Eventually, they actually crawled into the telescope. It was this big horn radio antenna. They evicted the family of pigeons that lived inside. They scrubbed off the pigeon poop, and they still had this signal. And at this point, this is the time when you just start like rolling into work real late and drinking a lot of coffee. And they're like, what? I mean, this is just, we have no idea. And one of their colleagues goes, you know, I heard this thing from these guys at Princeton. It's like, oh, and there's like, yeah, maybe you're listening to the universe. And they're like, shut up. It's probably pigeons. So it wasn't pigeons, it was the universe. And the guys at Princeton who were trying to develop the perfect experiment to record it were a little sad to see the pigeon poop scrubbers get 2 Nobel Prizes. So you think you had a hard day? All right, and you can see here, these are actually experiments that have been used to measure it. We use satellites here. And what's especially interesting, is that actually the CMB is not flat. And as we've moved to better and better space telescopes, what you see are fluctuations in the temperature of the cosmic microwave background. Not by very much, but things are a little bit hotter and a little bit cooler. So we'll keep that in our mind as we look at our universe. The next relevant Nobel Prize, because that's the best way to organize your talk, the next relevant Nobel Prize comes from understanding that the universe is not only expanding, but is accelerating. Now, I don't know about you, but an expanding, accelerating universe, frankly, is insane. It's a terrible idea, and whoever designed it really should reconsider. Often in science, what you find yourself thinking is, probably I got this wrong, or I'm going to get a Nobel Prize. Well, for most of us, it's going to be option A. That's really all of graduate school, as far as I can tell, is, you know, you run into your advisor's office and you're like, you'll never imagine what I discovered. And it's like, that you don't know how to plot? No, I see that, thanks. So here we have work that was done by 2 groups simultaneously studying supernovae in the late 90s and the early 2000s. Supernovae, type 1a supernovae, are fantastic. They're standard candles. This means that when a type 1a supernova goes off, it explodes with the same amount of energy in a different galaxy, in a different place. Every time they do it the same. This is fantastic. Standard candles are really important in astronomy because we can't travel places, and because every time we put a cosmic ruler on Kickstarter, nobody gives us money. So we have to have other tools. Luckily we do. So you can use a supernova in the same way that you might use, say, a 100-watt light bulb. I know how much energy a 100-watt light bulb gives off, and I could, send another savvy volunteer running down 6th Street, and then I could get a drink. But if I paid attention, I could figure out how far away they were by how dim that light bulb was. So people were using supernovae in this way for a while, and the challenge here is that when you're looking for a supernova that's quite far away, you can imagine they get pretty dim. It's hard work. So 2 different groups are doing this work, and they're trying to figure out, and we know some things about cosmology, and they're making these lovely plots. And what you might notice from this plot is that actually, perhaps those dots aren't exactly where we expected them to be. So after checking with a lot of other people, because you don't really want to be the one that publishes a paper that's like, the universe is completely different and surprising, and oh my God, we forgot to take that into account. So sorry, don't ask, we'll fix it. What they found was the universe was expanding and accelerating. And that's really strange. It's not something that people had necessarily considered. It was a surprising discovery, and it tells us that our cosmology, or our conception of cosmology, is very different. We could imagine a balloon to try to imagine our expanding universe, but if I'm honest, a balloon is really not that helpful. So we're going to look at some plots. Honestly, they're a little vulgar, but you'll just have to get behind them. So there are different ways the universe could appear. It could be decelerating. That could lead it to sort of expand and then crash back into itself. It could just sort of coast there for a while where it just goes on forever. That's what people thought was happening for a while. Or we could have this really upside down cakes universe where things are moving away from each other faster and faster. So just sit with that for a second, because when you think about things accelerating, there usually needs to be something accelerating them. What could possibly be accelerating us in the universe? This is another way to look at it. This is sort of edge on. You have time going this way from the Big Bang. This is things getting sort of further apart with the scale of the universe. And here is what is just honestly really bothersome about cosmology, if I'm frank. We actually live in different eras in cosmology. The universe is behaving differently at different times. Now, I don't know if you guys recall any physics classes in your lives, but we like to tell you that everything is the same everywhere all the time. We are liars. Much like the Bohr atom, that's true mostly. It's true on all the scales that we experience. But it turns out, if you could travel back in time, not so much. So here we have this interesting time at the beginning where the universe is matter dominated. That means matter, otters, whatever. That's the way things work. It's a little more intuitive, actually, to the way that you might imagine the universe to work. Then we come to this weird time with acceleration. Suddenly, the universe is accelerating. It goes from a universe we might think makes sense to the universe we live in today. Another way to conceive of that is the universe undergoing a tug of war between dark matter and dark energy. So early on, matter is winning this tug of war, but now dark energy is winning. All right, so I promised you a little bit of information about observations and theory. It turns out we're all just playing a giant dark energy edition game of Guess Who. It's very exciting. There are a great number of theories. More pop up all the time. I would say, it's whack-a-mole. It's as fast as the observers can knock them down. So there are many different theories to try to explain how the universe manifests itself, how dark energy is happening, why we're seeing this acceleration. They all sort of splinter into an infinite number of theories. Some of them are fairly straightforward, like the cosmological constant, which was introduced by Albert Einstein, who hated it because it was inelegant and stupid. And might be right. Wouldn't that be funny? At least he's dead. So modified general relativity, right, which weirdly on this list is perhaps not even such an outrageous suggestion. There are theories like dark fluids and quintessence in a holographic universe. And what we do, the way that we play Guess Who, is that we make observations. And every time we send up a new satellite or make a new observation, we're able to determine how much closer we've gotten to a theory that's accurate, that describes what we observe. So the cosmic microwave background, we're observing way back towards the beginning of the universe. With supernovae, we're observing things that are relatively close by to us. And what's interesting is, even as we build more experiments that do similar things, we see these incredible results. So this is from a recent satellite called Planck. And here you can see that as opposed to just being flat, the universe is really quite bumpy. And in fact, there's this big cold spot in the sky. And many people have hypothesized that this bumpiness is actually what gives us this interesting and varietous universe that we live in with all of these wild galaxies colliding and exoplanets, but that it's actually the bumpiness of the CMB that indicates that our universe, if it had been sort of flat and uniform, may not have formed in the way that we experience it now. Now, because, we're scientists, so we have to encourage you to be excited about what we're doing. I'm actually not a cosmologist. I just play one on this stage. I'm an experimentalist. So I'm involved in a project called the Hobby-Eberly Telescope Dark Energy Experiment at McDonald Observatory. And we're upgrading the 10-meter telescope. It is in the process of coming online. And we're bringing a fiber spectrograph, and in the process of building a fiber spectrograph with over 30,000 fibers. So we basically take 30,000 rainbows every time we turn it on. We're going to observe a ton of things. Primarily, we're looking at almost 1 million Lyman alpha emitters. These are young galaxies. Here you can see our fiber feeds. They're just exciting because they're tiny and they cover the sky all over the place. We're going to observe lots of galaxies, but these Lyman alpha emitters allow us to measure baryon acoustic oscillations. So that was the last part of that plot I showed you. The baryon acoustic oscillations can be thought of like echoes in space-time. And we're trying to isolate a time for dark energy that's right about at the peak of star formation. So for those of you that follow along, redshifts of like 2 to 3. And what we're doing is looking to see how space-time is distorted at this particular time. And you can see here, here's the analogy. Hold with me, I know we're 3 talks in. Christmas lights, right? You guys, like those weird net Christmas lights that are a terrible idea but seem like they're time savers? Those. Imagine those in your head. You know how far apart kind of all the Christmas lights are, and then you go and throw them on your Texas sage books, and it does not look anything like it should. But they've moved to different distances, right? And you turn them on, and maybe you don't know you're looking at a Texas sage bush, but you know that it's not flat. So we're going to use Lyman alpha emitters, these bright star-forming galaxies, in the same way. We observe 700,000 of them, and we look at how they're distributed. So even though we can't measure dark matter directly, we can look at how these galaxies get distorted, and that sort of allows us to cheat, right? It's like when you see in the movies and you throw the powder so you can see the laser, right? Like that's what we're doing. This is us, except we can't get out there because, again, cosmic ruler can't travel through time and space, pain in the ass. So instead, we use these galaxies that are already in place. So you can see here, life is really elegant. It mostly just involves hitting things with hammers. They're really high precision hammers. And Rachel actually asked, what does my job currently have in common with building sailboats? And the answer, humorously, that I had not thought of until I talked to someone earlier today, it takes place in a Tyvek suit. Some shocking length of my life has been in a Tyvek suit, which is funny because Rachel picked that video picture without knowing that, but that's basic. I could just wear that every day. I'd be like, oh, hey, that gross sweaty white suit, that's my life, thanks. So I crawled around in sailboats. Now I crawl around in a clean room and less things explode, which is better. And obviously, not by myself. We have a lot of staff and a lot of undergraduates who have helped make this happen. Here's some of the spectrographs before they go out to the telescope. And just for the astronomers in the room, because otherwise I'll get in trouble, obviously measuring things like dark energy is going to happen from a lot of different experiments. So here are 2 of them, SPT, obviously at the South Pole, and EBOS. They're looking at different redshifts and measuring dark energy in different ways. There's a great experiment called DECAM that's gone in Chile on one of the big telescopes down there. So to pin down a mystery as big as the history of the universe is going to take a lot. Right? This is a lot of resource to, we're probing all of time and space. It's like writing a biography for the entire universe. So here's our takeaways. Dark energy, something we're making up. No, something is distorting the universe in ways that we don't really understand. So theorists come up with a lot of ideas to try to explain the observations, and then observers go back out and measure them to try to eliminate what they don't understand. So that's astrophysics. Now you guys can do it. You have the Googles. Yeah, I'm totally feeling it. So to go back very briefly to what is dark energy, a few of you brave souls came up with answers, and afterwards you should come and get prizes for me. So here are the 2 that are my favorites. There are a bunch. The first one was, this is good, regular energy going through some tough times. Oh. You guys are so kind. Yeah. So if that's yours, you can come up here. And also, dark energy, where the cookies are, which I also feel real good about, because snacks and otters are all the way. Awesome. Well, you guys have been fantastic. I hope you have a good rest of your night. And let us know if you have astrophysics.
All right, so we have some time for some questions.
Oh, really? Damn it. I thought I filled it.
Over here on the stairs.
How do you say that there's, the dark energy is like 74% and matter is 5%? Where gives you the relative number?
Yeah. So although I made a joke about accounting, so the question was, how do we do the universal energy budget? It's a good time to get a drink. The short answer is a lot of different ways. So it's a combination of many experiments that are measuring things like energy density in different places in the universe. If you wanted to see technical details, there's actually a fantastic paper that collects all of the experiments and compares them with errors to try to sort of determine kind of what the total expected energy is and what kind of energy we see in things like, because for a while, just for some context, people thought that maybe dark energy, maybe we could fill the gap, right? Dark matter has undergone this as well. Maybe we're just not thinking of it, right? For a while, for dark matter, people were like, maybe it's just brown dwarfs that are really secretive. Maybe it's real cool stars that are far away that we forgot to look for. So, there have been many of those experiments that have kind of explored what we'll call the more mundane answers. But so it really involves kind of all of the fields of astronomy coming together and accounting.
Okay, is there a question over here?
How do you have acoustic oscillations across a universe that's mostly vacuum?
That's an interesting question. Yeah, but once I can answer it, I'll let you know. So the question was, how do you have baryon acoustic oscillations when we don't have sound, right? When you're talking about a universe, you don't have a lot of sound traveling through space. I think my short and quick answer is, it's more of an analogy than an accurate description. Yeah.
Why that?
Yeah. I'm telling you, we're terrible at naming things. It's really shameful. Oh, straight upstairs?
Straight ahead.
Okay, I can't see because of the lights, but I'm told over there somewhere.
Upstairs.
Oh, by a red light. Cool.
Why do we think that we can see everything? Because so if we think about looking in every direction, would we see just about the same distance in every direction? And then if we're not in the center, would there be a little bit that we can't see?
So the question was, why do we think we can see everything? Because we're cocky bastards. What other answer is there to that question? The slightly less obnoxious answer is that, so if we can't see it, we don't care. That's a science answer. Things exist because we can measure them, right? So if we can't measure them, I think your answer is more like, the dark side of the moon, which we got a lovely picture of the other day, I'll note. So I think the answer is there's not places that are lurking in the universe, but you do bring up an important point, which is, often people have described dark energy like vacuum energy, this idea that there maybe is something outside the universe that we measure that might be pulling outwards, right? And that's definitely possible. And there are theories that often meander into the land, like string theories, that are very difficult for us to actually make measurements of. So as an experimentalist, my slightly obnoxious answer is, it's really beautiful math until you give me something that I can eventually observe. Now, of course, we don't always have the technology to make the measurement, but you have to at least give me something to measure.
Okay, is one at the back
I
over
have my
here?
sunglasses in them.
So, it's slightly off topic, but it was in your talk.
That's cool. Is it about otters? I'm real good on otters.
One of the things I've always been curious about is, does the expanding universe imply that the value of time varies with, does time get slower or faster with the expanding universe?
No. I love just answering things that way. No. One of the complications of being an astronomer is that we talk a lot about the past that we can't go to, which means that they're sort of talking about what we can measure and talking about what one might experience, and those things are often different. So, I think the shortest answer is I have not spent a lot of time thinking about, like, if you were at the Big Bang, what that would feel like. But I'm not, I'm sticking with my no answer. Yeah. Oh my God, someone's jumping. Yeah, you go because I don't want you to fall out of there. Sit down, it's very dangerous.
Because the universe is expanding at an accelerated rate,
Yeah.
is it possible that at some point intelligent life might deduce that they're below the universe?
Definitely.
Also, is it possible that we're currently already living in a time when we don't really have the ability to completely understand the universe?
So that was a two-parter for you guys. The first question was, is it possible because of expansion and acceleration that intelligent life might eventually think that you're alone, right? That like we lose contact? Is that a fair summary? So the short answer is yes, right? I mean, unless we get better at communicating and sort of can breach the speed of light, which we can't, which is a bummer for everybody, there's definitely a time at which everything becomes isolated, right? Where light, our light doesn't get to anywhere else and we don't get any other light. And you look up and it's dark and sad and hopefully we'll all be dead by then. They'll look at pictures and be like, wow, people on Earth were drunk. Look at all those things they drew in the sky. Astronomers, stupid. What'd they study? Beer. So that could happen. In terms of intelligent life, so I actually think Rachel touched on this a little bit earlier, which is when you're trying to study or even like conceive of, is there life on another planet or what does intelligent life look like, you have to decide what you're looking for. And there's actually, quite extreme prejudice as we decide what we're looking for. So clearly we look mostly for life that looks like us. Right? And there's some great, there could be like a whole film night of we're freaked out because aliens aren't like us and then they're probably coming for us and it's terrible and there's a misunderstanding and then we have a war and wow, that was a mistake. So there's of course other movies that are like we're so peaceable and we hug everyone and then we all die in a mass extinction event. So, decide which side of the coin you're feeling tonight. But, I think that there are, as we think about intelligent life and extrasolar planets and what that means for us, I think it's actually a great opportunity for sort of our philosophy to really kick in and think, as we ask scientific questions, we absolutely are bringing our own expectations and sort of prejudice to those questions. So the way we ask those questions comes from what we expect and what we understand. And nothing gets more that way than aliens for sure. And I have to assume if there is other life out there, that other life, although in some wonderful world would be much more advanced than us and be super civilized, is probably just like, oh, that planet looks like a bit of a mess. We'll give them a few centuries, they can call, we'll bury something, it'll be fine. So I think that there's definite complications when you think about different ways that civilizations could develop, even if we could get in contact or they're close enough.
Okay, we have to wrap up, but Dr. Tuttle will be around, I hope, a little while, if you want to find her and bug her with more questions.
So late.
Okay, so thank you very much.